Thanks a lot for the nice invitation. It's really a pleasure to be here. Today I'm talking about a very classical theorem, Hochschild-Kostant-Rosenberg theorem, in the context of differential geometry. It's a theorem that somehow connects different objects, connects multi-differential operators and multivector fields. And let's say what I will try to convince you is that we found an improved version of this theorem, improved in different ways. Improved first because, let's say, we found a global proof, so much cleaner, so we don't need to go locally and then globalize it. And also, let's say, our version is kind of highly adaptable. So I will try, if I have time, to also show you some new applications. As you can see, this is a joint work with Jonas Schnitzer and Stefan Waldmann, and recently appeared on the archive. Okay, so very, very roughly the outline of this talk. As you can see, it is divided in 3 steps, 3 sections. Section number 1, motivation. So why am I interested in this theorem? And somehow the motivation comes from deformation quantization. So I will give you a very fast and rough idea of what deformation quantization means, what it is, why do we need this theorem, why do we need HKR. And then once we have this in mind, once we have clear why we need that, I will state it. And then we go, let's say, to the improved version. So the second section is the main section of my talk. And as I said, I'll try to really dig into the proof. So I will essentially introduce you a couple of new techniques, a couple of techniques, symbol calculus and Est-double complex. I say not new because this is somehow also the advantage of the proof we have of HKR. I mean, the techniques we use are kind of easy and well known. So it's just, I would say, the tricky part is to get the idea of using symbol calculus, and that's it. The trick in some sense is this one. And then, time permitting, I will go to applications. So I can show, there are more applications. I just show you a couple of them just to give you the taste of how adaptable is my proof, our proof. So first, HKR for submanifolds, which is not really, I would say, not really a new application. It's more like a sanity check that I will give you. But second, the G-invariant HKR, this is really, as far as I know, new result, new application. So I really will show you that out of the nice functoriality property that I have, I can go to G-invariant. So Lie group action and G-invariant HKR. Okay, but let me enter in the story. So let's start with the motivational part. Okay, so what do I mean by deformation quantization? And first, let's say, what do I mean by quantization? Quantization just means that I want to pass from the classical to the quantum realm. And there are different programs to do that. So here we do focus on, let's say, the main difference of the formulation of a classical and quantum mechanics is in the algebras. So classical mechanics somehow is encoded in what? We have a phase space, which is a manifold, a smooth manifold, with a Poisson structure in it. And what we do is passing to the algebra, so observables. Okay? So smooth functions on my manifold. This is a commutative algebra because we have a pointwise product on it. And more, we have a Poisson bracket. As I said, we have also manifold. Important because it, how can I say, help us in describing the dynamics. Because I want to write a Hamiltonian equation of motion, and Poisson bracket helped me to do that. Okay, so, after all, I can resume by saying classical is commutative algebra. Let's go to quantum. So generally, quantum is something completely different. Generally, you have a special class of operators. Generally, you have a Hilbert space, which is your phase space, and then some classes of operators, like bounded operators, for example. And they form an algebra as well, which is non-commutative. But now you see it's very different from what I start with in the classical realm. So this, let's say, very strong difference is kind of bad if you want really to pass from classical. Can I actually find a suitable non-commutative one, which is a deformation of the classical one? Oh, sorry, no. Okay. And when I say deformation, I do mean formal deformation. Okay? Formal means I don't care about convergence, morally speaking. Okay? So meaning what? In the quantum setting, now I focus on formal power series on the vector space of functions on my manifold. And I do deform the product. So I have, you see, a product that now starts with the pointwise product, and then I add a deformation term, which is just an infinite series. As I said, I don't care about convergence. Okay, it's formally convergent. And what do I have here? Mu k, this is just a bunch of B differential operators. And the first one, mu 1, is related to the Poisson structure. Okay, so let's say, what are we doing? We are trying to connect to get a deformation of a formal deformation of the pointwise product in the direction of the Poisson structure. And if you keep in mind what I told you at the very beginning, I mean, the Hochschild-Kostant-Rosenberg is a theorem that connects multivector fields and multidifferential operators. Here I have a Poisson structure, which is a bracket, or in other terms, is a bivector field. And on the other hand, I have B differential operators, and I want to connect them. So this is why I somehow encounter the need of connecting these two objects. And you will see, I mean, the story of quantization is way more complicated than that. But let's say this is a first step. Okay, problem. Problem is associativity. If I want to study associativity of this deformed object here, I end up in writing down an infinite chain of quadratic equations in mu k. Not funny. So what do? Okay, I can use a beautiful theory developed by Gerstenhaber, which is the theory of deformation of associative algebras, which is, let's say, the aspect I'm focusing on at the moment. So,
the fact that mu1 is the Poisson bracket is a consequence or a request?
I mean, this depends on, let's say, on the way you put. I mean, generally you start with a request, but actually, I mean, after all, you see that this is a consequence. Okay, so we move to a completely algebraic setting now. So I have an associative algebra that, yes, let's say in the case I was discussing before was the associative algebra of smooth functions on a manifold, but I can discuss in a completely general case. The Gerstenhaber theory is made for any associative algebra. And it tells you that the deformations are encoded in a special cohomology called Hochschild cohomology, which is the one I would like to compute. But let me enter a little bit more into that. Okay, so I have an associative algebra, and then I cook up a complex, this one. So I just take, you see, homomorphism with k inputs and one output on A. Okay, this is a graded vector space. And then we have more. We can define a differential, delta. And you see, the differential is defined in a kind of easy way. I mean, you have this phi, which is a homomorphism with k inputs. Okay, and then I want to define an operator delta that increases the degree, right? I want this to be a differential. So how do I do that? There are many ways. Okay, first I can say, well, I do apply phi on, let's say, the second k inputs, and then I multiply by the first one. Or the other way around, look at this one. I mean, other way around. I apply phi to the first k terms, and I multiply the last one. Or I can put all together, all inside phi, but then you see I have to multiply two of them. Otherwise, I have too much inside. So I do all this possibility, I sum them together, and what I get at the end is actually a differential. It squares to 0. Okay. So what else do I have? So I have a differential compatible with the grading, and I have also a product here called cup product. Very easy. I tensor two cochains, and then the result I multiply. Pretty easy. So at the end of the story, I get a DGA, differential graded algebra. Okay, let's go now to cohomology. What is the zero cohomology? The center of the algebra. So of course, if I have a commutative algebra, then it's the algebra itself.
The product.
The cup.
Yeah, the cup product.
Do
you then use cyclic permutations in the definition?
Yeah.
Yeah.
Yeah, thanks. Okay, so we have the center of the algebra here in the zero cohomology. So in the case we have, for example, the smooth functions on my manifold. There we have just the algebra itself. First cohomology, it's just derivations of the algebra modulo inner derivations. So something, again, pretty easy. Second cohomology becomes interesting. Infinitesimal deformations, meaning what? Meaning I have equivalence classes of deformations which are associative up to the first order. Okay, but I would like to extend it. I would like to go to the next order. Can I do that? Sometimes yes, sometimes no. It depends on this cohomology, on the third cohomology. So this gives you the obstruction to extend this infinitesimal deformation to the next order. Okay. So, I hope I convince you that, let's say, this is what we really want to study, Hochschild cohomology. If you want to, let's say, study the deformation of associative algebras, you really have to dig into Hochschild cohomology. And then let's see in particular, in the case of our algebra, what happens. So if my algebra is infinity of M with the pointwise product, and I'm not interested in the full cohomology, but just because you remember the mu k were just B differential operators in the deformed product. So I'm, let's say, more interested in a subcomplex, the subcomplex of multi-differential operators. Okay, and I would like to compute now the cohomology of this subcomplex. The theorem of Hochschild-Kostant-Rosenberg tells you that there is a quasi-isomorphism with multivector fields. Okay, and I can show you, I can tell you that the formula is also rather easy. Here, sorry, there is a mistake. This is not the cap, this is the real multiplication because it's evaluated. Okay. Anyway, so you have a quasi-isomorphism, means you have an isomorphism in cohomology. Okay, so just a couple of things. First, I cited, let's say, the original paper, so Hochschild-Kostant-Rosenberg in the 62. This was actually done not in differential geometry, but in algebraic geometry, so in a completely different setting. But then there were sequent works that proved the, let's say, this differential geometry version of the theorem. Point is that, let's say, all the proof I could find of this theorem had some drawbacks. First, they were local. So local means that you really choose charts, and then you choose coordinates, then you compute your cohomology in coordinates, and then you have to globalize, meaning gluing together. It works, but there are situations in which gluing together is not obvious. For example, remember what I told you at the very beginning in the outline. I told you I would be interested to see what happens whenever I have a Lie group action and I want to look at the G invariant case. And there the situation is more complicated. So gluing in the G invariant case is more complicated, it's not obvious. Okay, so second problem, I have a quasi-isomorphism here, but I don't have the quasi-inverse, meaning I don't have the inverse in cohomology in this theorem. Or also, which is somehow very much related, I don't have the homotopy, because whenever you have quasi-isomorphism, it is the homotopy who tells you in which sense a quasi-isomorphism is a quasi-isomorphism and not an isomorphism. So what is the failure, let's say, to the invertibility? So the idea that we had was exactly to take care of these problems, of these drawbacks. So having as a goal a global proof directly, plus having the quasi-inverse and the homotopy for this theorem. Okay. So let's give a look to the improved version, how this actually looks like. So you will see that what we get is actually a retract, a deformation retract. So we will get HKR, yes, global, but of course recovering the usual formula, okay? We will get the quasi-inverse, the homotopy, and the formulas you will see are gonna be very explicit and also rather easy to write. And as I told you, this is really adaptable because this retract has good factoriality properties, so I can move to many other little cases so I can apply this to many situations. Okay. Now, let me try to give you a first rough idea of what the proof is. So what is the strategy? So my goal, the first goal I have in mind is to cook up this arrow, this quasi-isomorphism. So from multivector fields to multi-differential operators. Okay, so on the right, what do I have? Okay, I have, let's say, the idea that I can somehow get rid of geometry. How? I can somehow get rid of geometry because I can think to multi-differential operators just in terms of their symbols. And this allows me to identify the cohomology, so the multi-differential operators, with the complex, which I called co-algebra complex, over vector fields. So moving completely the information that we have out of geometry into an information which is purely co-algebraic. And once you have that, so you get rid of geometry by, as I said, let's say, looking at symbol calculus, so symbols of multi-differential operators, then you want to actually compute this cohomology and not this one, but this one. And here, let's say, the steps are purely, again, algebraic or co-algebraic. Meaning what? The idea is that I want to relate this new co-algebra complex with the Chevalley-Eilenberg, because Chevalley-Eilenberg on vector fields is exactly given by the Grassmannian algebra of vector fields, right? So multi-vector fields. So how can I do that? I can do it with a, let's say, a meta step. So I connect them with a double complex, which is called Van Est complex. These two arrows, I will show you, they are quasi-isomorphism. And this means that at the end of the story, I also get the quasi-inverse and the homotopy that I want. Okay, so let's try to, so this is, as I said, the rough strategy. Now let's try to go a bit more precisely into the story. So step number one, let's say the geometry part. I want to get rid of geometry. How can I do that? So roughly, the idea is that I want to associate to a differential operator a symmetric vector field, essentially. So how can I do that? I do choose a covariant derivative. And once I do that, what I can do is associating, constructing this new map, D nabla, which you see, it just take a symmetric tensor product of one forms and increases the degree by 1. I wrote you the formula here of this map, not that it's relevant for the talk. I mean, you can just forget it. I just wanted to point it out that this map is really easy to construct. So out of the covariant derivative, it's nothing hard. Sorry, torsion free. Not in general. No, not in general. Okay. And then, okay, it's easy to construct this map, but it's very interesting because it allows me to get the symbol calculus. This is something that in my knowledge, let's say, comes back to Palais, 65. So let's say gives you an isomorphism, which I call OP, from the tensor algebra of symmetric algebra of vector fields to multi-differential operators. And again, you see, it's also not hard to write down. I mean, this is your tensor algebra part. You want to see as a multi-differential operator, so you evaluate on functions. And then you see what you have on the other side. You differentiate, let's say, your F1 function, for example. How many times? It depends on the degree of your vector field. Okay? And then you symmetrically insert X1, and then you just multiply all together. So it's rather easy to write down, and you get your multi-differential operator. Okay, so as I say, nothing new, nothing really complicated, but we have to be a little bit careful with the structures here. Because you see, I mean, on the right, I have multi-differential operators, where I told you I have a differential, because we have the Hochschild DGA. What about the tensor algebra of symmetric algebra of vector fields? What is the differential over there? Because after all, we want to compute a cohomology. So we want to know what is the cohomology over there. Okay. So let's go to a very general case. So I will show you that we do have a differential and also, let's say, a special one, something we really like. Okay, just let me introduce you to the complex I was talking about, coalgebra complex. So I consider V as a module, generic, okay? So in my case, it's gonna be vector fields, but this can be done in a completely general case. SV in general is a coalgebra because you can define, you see, a co-product, co-commutative, co-associative, again, in a very easy way. This is called shuffle coproduct. Shuffle, because you really take, you see the object from your symmetric algebra, you divide in two and you symmetrize both legs independently, essentially. Co-unital, because you have a co-unit, meaning just you project down to symmetric degree 0, and that's it. I need to, let's say, cook up another coproduct, which is called reduced, just taking the one I gave you above and removing the part in which the x only ends up on the right or on the left. So out of this, I can really construct a complex, meaning I take a tensor algebra of the symmetric algebra V, and now I have to give you the differential that I was aiming at. What do I need to do? I mean, I have a coproduct on SV, and I have to extend to the tensor algebra. What do? I simply extend as a graded derivation, and I have a differential. Okay, so this is my differential. The funny thing, I would say not even funny, I mean amazing thing, is that now if the V is the V I am considering, so vector fields, the delta I have here is exactly the delta that corresponds to the differential, the Hochschild, let's say, differential, via this op isomorphism. So they are really connected by this isomorphism given by symbol calculus. So there is a really great correspondence of differential structures. Okay. Let's go back to the idea of the strategy. So geometry part is done. Geometry part is done because I really, how can I say, I really identified my complex with the new complex via the op, because I also connected the differentials, not just the graded vector spaces. Now I have to go to the coalgebra part. So I really have to compute the cohomology of this coalgebra complex. Let's see how. And now to do that, I need to introduce you the Van Est-double complex. This, again, it's something that, from my knowledge, comes from a definition from 53 or something like that, so well-established theory. And how do we construct this double complex? It's very easy. You see, you take the tensor algebra of a symmetric algebra of your V, whatever V is, again, generic A module. You tensor with another slot of SV, and at the end you tensor with the Grassmann algebra. You see, it's bigraded because you have a degree here in the tensor algebra and a degree here in the Grassmannian. Okay, so we can think, of course, as the usual grid. Okay, so this is my big complex, the Van Est complex, and I would like to connect the double complex first with the coalgebra complex I just defined, and then with the Chevalley-Eilenberg complex, which is at the end of the story my, let's say, goal. Okay, let's see what happens with the coalgebra part. How can I connect the double complex with the coalgebra? I have very easy maps. I have injections and projections, J and Q. Let me just write the formulas. Yeah, very easy. So injection meaning just I put the second part to 1. So symmetric and Grassmannian to 1. And projection meaning I just want to end up with this guy. So I use the co-unit. Oh, no, sorry, the other way around. What did I say? This is the Grassmannian, yes. So you see, I have very easy maps that really connect the double complex with the CA complex. Okay, but what about the differential? I mean, these are sure, obvious morphisms. We have to see what kind of properties they have. Okay. Let's see the differential. The differentials is also pretty easy. Okay, you see, you take an element, so X is in the tensor algebra, phi again is in the SV slot, and Xi is in the Grassmannian part. Okay, so X remains completely untouched. And then what you want to do? You want to increase the degree of the Grassmannian part. So the part here is going to be always the same. You move legs back and forward, essentially, using, let me remind you, the Swidler notation that I use here. So this is a coproduct, so it gives you two legs. Right? So you see, I took the second leg, phi1, and moved to the Grassmannian part. Yeah, I mean, I have to project, you know, so that the wedge makes sense. But okay, modulo this part, I just moved back forward a leg. Okay, so this is a differential. So now question, can I actually now compute the cohomology? I mean, the row cohomology? The answer is actually yes, I can. I can compute the row cohomology. It's rather easy, and I can show you that actually I can give you the homotopy that gives you what we want. That gives you the cohomology. Why that? I mean, again, what is K? K is a homotopy map, meaning that you want to now decrease the Grassmannian degree. So you see what I do again is moving back a leg to the SV slot. Okay. So we now decrease the antisymmetric degree. So this is K, this is a homotopy, meaning also that J and Q are quasi-isomorphism. So we have what? We have that the row cohomology is concentrated in the grid 0 and is given by the CA. Right? So, I mean, of course, let's say how can I say, the respective degree in the CA complex, in our coalgebra complex. Okay. But now what about the vertical direction? So we have, let's say, connected this double complex with our coalgebra complex, and in particular the cohomology, which is what we wanted. What about the vertical direction? Vertical direction is now relating somehow this double complex with the Chevalet-Eilenberg. Let's see how. Again, very similar story. We have very easy maps, I and J, injection and projections. And then we have to cook up a differential. Sorry, here, maybe, oh, sorry. Here, this is a coalgebra differential. What do I mean? What do I have to do here to get a differential? I have to now increase the tensor algebra degree, right? So if I want to increase the tensor algebra degree, I have two possibilities. Either I act on X with the co-algebra differential. Here it is, first one. Or I simply, again, use the usual trick to move legs around. So I take, let's say, the shuffle coproduct, and then I take the leg from here to the first, to the tensor algebra component. And then I sum them together, and again, I get a differential. Okay, so this is my, my differential. It does its job, so it increases the tensor algebra degree. And now, what about, and now what about the cohomology? Also in this case, same story. We compute the homotopy. Here it is. So you see, you have your tensor algebra part over here, x1, xk. And here what we do is simply, this is kind of a, I don't know, I would say a trick. So you move the last part of your tensor algebra part to the SV slot, so the middle slot, and then you project phi away. So this is your homotopy. But same story, this makes IMP quasi-isomorphisms with respect to this homotopy. And this also tells you that if you want to now compute the cohomology with respect to this differential, what you get is the Chevalley-Eilenberg, term by term, I mean degree by degree. Okay, and now we have to put all together, because after all, what we wanted to do was connecting the blue part with the pink part, right? So the coalgebra with the Chevalley-Eilenberg. And we want to do it via the Van Est. But now we have a problem. We have a problem because you see, CA is, yes, related to Van Est, but with respect to a differential. And the Chevalley-Eilenberg is related to Van Est, but with respect to another differential. So we would like to, let's say, use a common differential, which is this one, which is the total one, the one of the double complex. Okay, problem now is that if I do change the differential, everything gets completely destroyed. If I change the differential, I mean, homotopy are not homotopies anymore, and quasi-isomorphism are not quasi-isomorphism anymore. So I really have to, let's say, and even cochain morphisms are not cochain morphism anymore, right? If I change the differential. So I have to fix this situation. How can I do that? I have a very well-known tool that helps me out, which is the homological perturbation lemma. Okay, so what is very fast, let's say, what is homological perturbation lemma? You have a retract, meaning you have two complexes, C with its differential, D with its differential, quasi-isomorphisms, and homotopy. And now you can see even explicitly what do I mean when I say quasi-isomorphism. You see, I mean, I have P and I composed, gives me the identity, but the other way around, it's not. It's not, but its failure, so the failure, let's say, of the invertibility is controlled by the homotopy. Okay? So this is a retract. What can I do? I can perturb it in a way that, let's say, gives me now another one, another retract. Meaning what? I take B as a perturbation, so that, let's say, if I sum D, the differential of D with B, it's again, this is again a differential, so again squares to 0. The perturbation needs to be small, meaning that the identity plus BH has to be invertible. And when you write down the inverse, it gives you this term. Don't be scared about this infinity. When you really evaluate it to elements, it turns out to be a finite sum. So let's say under this hypothesis, what you get is a new retract. You see everything is deformed, is changed. We have a new differential, new injection and projection, the differential that I perturbed here by B, and a new homotopy. This is homological perturbation lemma. And you see, I don't want you to, let's say, focus too much on formulas, but what I just want to show you is that you really have explicit formulas to write down the perturbed ones. So big H, so the new homotopy is given by the old one plus the new term, the perturbation term, let's say. Okay, so the idea that we used is due to Menrenken and Salazar from 19. So the idea is really to perturb the Van Est-double complex. So we take, you see what we have. We have our two retracts here, the one that connects the coalgebra complex without any differential with the Van Est, and the one that connects the Chevalet-Eilenberg, no differential with Van Est. But keep in mind what happens with the differentials. So 0 here is related to, let me remember, with partial, right? Yeah, with partial. And 0 here is connected with delta via this maps, the quasi-isomorphisms. So now we look at partial as a deformation of delta and delta as a deformation of partial, and we see what happens. And we apply homological perturbation lemma. And something can, I don't know how to say, a bit miracle happens, I would say. Okay. First perturbation. I look at partial as perturbation of delta. So what happens is that you see the horizontal retract changes. So I have a new homotopy here, the big K. They both should change, but luckily, actually only Q changes and J remains unperturbed. And then you see the differentials are, this is the total one because I'm perturbing in this way. And here I have exactly what I want. So this is somehow, let's say, the nice part. Here I get exactly the coalgebra complex differential that we want, the one I want to compute. So this means that now I know exactly that the cohomology, the coalgebra cohomology is the same, because I have quasi-isomorphisms here, of Van Est cohomology. Now let's see what happens at the vertical. In the vertical direction, same story. We have, now we interpret delta as a perturbational partial. So the vertical retract also changes. Also here, the injection doesn't change, the projection does. The homotopy changes. And in this case, the differential, the Chevalet-Eilenberg differential does not change. Also very important, because this is exactly what we want. So putting all the information together, we get what they call Van Est deformation retract. So we could say we have now two quasi-isomorphisms, which we call Van Est, both, from the Chevalet-Eilenberg complex, cohomology complex, to the coalgebra one. And I have an homotopy. And as you can see, this is just combination of the perturbed maps. Yes, you have to write it down, but it's nothing too complicated. It's really something handleable, okay? So you see, you have your this composition, which is the identity. Other way around is not, but you have the homotopy controlling the failure of the invertibility. So now you can really say what you want to say. You can really say the cohomology of the coalgebra complex is the same as Chevalet-Eilenberg via Van Est, okay, but you can say they are the same. And now you can put all together. So you can really combine the symbol calculus over there, which was an isomorphism, the Van Est retract over there, and what you get is, as promised, the HKR with the homotopy. The HKR theorem as a retract. So you see, I got now the HKR map, which I can write just a composition of the op isomorphism and the quasi-isomorphism of Van Est. You can write it down, it's pretty easy, and you will see, you can check it very, very easily that this is the same as the very first map I wrote you, the classical HKR morphism I wrote you. This is new. So this is the quasi-inverse. And the homotopy, I didn't write it down, but okay. You can again compute, let's say, by using the technology I showed you before, right? The Van Est retract, essentially. So also in a very easy way, in kind of easy way. So let me point out a couple of things. So you see, I mean, as I promised, I got a retract. I got something which is completely global. I didn't go locally and then I had to globalize. So let's say I solved a little bit the drawbacks I told you at the beginning. What I want to point out is that at some point I told you I had to make a choice. I had to pick up a covariant derivative. What turns out is that HKR does not depend on this choice, but the rest, yes. So the quasi-inverse and the homotopy do depend on the covariant derivative that I chose. Okay. And you see, we have explicit formulas. Okay, I still have 10 minutes, so let me tell you now something about applications. Okay, so
So is the total cohomology of the Van Est complex that vanishes, I guess?
Sorry? The total cohomology.
Yeah, the diagonal one.
Yeah.
And then the horizontal one is isomorphic to the vertical one.
Yeah.
That is essentially what you did.
Yeah. Well, not me. Not me. This is Salazar and Maybank. Yeah.
Yeah. Okay. So, and the second remark is, you can also get the symbol calculus by looking at differential operators of order n, modulo of order n minus 1. So you go from the filtered algebra to the graded algebra, and this becomes mutative, and this is exactly the so you don't need the covariant derivative.
The covariant derivative. Ah, okay. Thanks. Okay, I'll think about many things. Okay, so applications. So first application, as I told you already, this is to me more like a sanity check. So consider now C submanifold of M, but I want this to be embedded, closed embedded submanifold. And I consider now a covariant derivative which is adapted to C, meaning essentially that if I restrict to C, I still have a covariant derivative on C. Okay, okay, so in this case, I do have some tangential symbol calculus. Okay. So this helped me to get a new version of HKR, which we call tangential HKR, which you see it's from, let's say, tangent vector multivector fields, so globally defined vector fields which on C restrict again to vector fields. And on the other hand, you have differential operators which are again tangent to C. So here, essentially, we did not to do, I say there is no big deal because you don't need to do much. I mean, you just have to ensure that you have symbol calculus. So in the case of embedded manifolds, submanifolds, you're sure that you have an adapted covariant derivative, so there is no problem. Otherwise, you have to be a little bit more careful, or maybe not. I will think about. Okay, because yeah, in my mind, if you don't have adapted covariant derivative, then you simply don't get symbol calculus.
Differential operators which respect the submanifold.
Yeah, thanks. Okay. Anyway, so second, somehow more important, is the invariant HKR. So consider now the situation in which you have a Lie group action, and then you consider a G-invariant covariant derivative. Now again, the ingredients are always the same. You have a symbol calculus, you have to ensure to get an equivariant symbol calculus, and then you have to, let's say, go to the Van Est machinery, right? Okay, there are, let's say, two steps here to take care. So first, the equivariant symbol calculus. I mean, this can be proved that you really can cook up an equivariant symbol calculus if you have a G-invariant covariant derivative. That's okay. I mean, and this is something, how can I say? I mean, to me, this is, from my knowledge, this is new, because what I know is that in the past, something similar has to be done only in the case of, let me remember what was, proper group actions, because there you have really the possibility of averaging, right? And then you have everything working. I mean, but in this case, you can look in a completely, let's say, general fashion. You have a Lie group action. You have to be sure, of course, it's not always the case that you have a G-invariant connection, but then you can actually get an equivariant symbol calculus. Second step is Van Est. And here, let's say, there is the nice aspect of also our construction, because our construction has some really nice, good functoriality properties. So this functoriality, as a, let's say, a subcase, as a special case, works for the invariant, for the G-invariant Van Est. So this means that I have also, let's say, Van Est map that commutes with the action. So let's say putting the two things together, the equivariant symbol calculus and the Van Est maps commuting with actions, we do get invariant HKR. So as I say, there are more applications. This is just to give you a little bit the taste of what's going on. Of course, since I'm here, since I'm talking about Lie group actions, the obvious step is talking about Lie algebra actions. And here, essentially, the stuff is really the same. I mean, you really use the same kind of techniques. I mean, now G-invariant in the sense of Lie algebra, you have to take care. So equivariant symbol calculus in the sense of Lie algebra works essentially the same. And the functoriality works really the same. So it doesn't really change much. So I have both invariant claims for the HKR theorem. And I think I can simply stop here.